Here in section 5.2, we talk about the basic rules of probabilities and just sort of begin the foundations of calculating theoretical probabilities. Okay, so in 5.1, we use simulation. We use random digit table, sometimes roll the dice. But in order to get our simulated probability to even be close to the theoretical probability, we'd have to take lots and lots and lots and lots of simulations, right? Lots of trials. So here we want to start talking about what a probability model is. And a probability model involves sort of two things. So first, the sample space, which we denote as a capital S, just the symbol we use to denote the sample space. And the sample space is sort of the list of all possible outcomes in a particular situation. So it could be the list of the 52 cards in a deck of cards, or it could be the 6 numbers on the sides of dice, right? When I roll a die, what are the outcomes? So you list all the possible outcomes. Now, sometimes all the outcomes are equally likely, but sometimes they're not. And so the probability model as a whole will involve the sample space, S, and then also sort of like the list of probabilities for each outcome. And so sometimes when they're, in particular, when they're not all equally likely, then we will often put it in the form of a table. So we'll put like the outcome, and then underneath it, we'll put the probability of that outcome. But together, that information forms what we call the probability model. All right, so here's an example. If I roll 2 dice, so you can see I have 2 dice here. To help facilitate thinking about this, it's best if you think of like 2 different colored dice. Like in this case, I have sort of a brown or tan die and then sort of a greenish die. And so the sample space is what's listed there, right? There's 36 possible outcomes when rolling 2 die. And then if the dice are fair, in other words, they're not weighted in some way or, somehow cheating dice. So if they're fair dice, then each outcome is equally likely. So the probability you'd get any one of those 36 outcomes is simply 1 out of 36. All right, so probability models allow us to find the probability of any collection of outcomes. So it was easy when we looked at that, the sample space for those 2 dice, we can very easily pick out what's the probability of one of those outcomes. But what if we said something like the probability of a sum of 2 dice? So we'll get to a little bit more complicated events in a minute. So an event is just a collection of possible outcomes. And an event, generally, we use a capital letter, not S, because S is used to denote the sample space or the list of all the outcomes. So an event is a subset of the sample space. And so we'll use a capital letter like A, B, C, and so on. All right, and then we write it as like P of A. It looks like, like some kind of function notation like you might see in algebra. But P of A just means the probability that event A happens. So if we define dice rolling, so 2 die, and if we define the event A as the sum of the 2 die is 5, then this is the list of the 4 possible outcomes, or that subset of the sample space. So A is that we get a sum of 5. So what is the probability that we get when we roll 2 dice that we get a sum of 5? Well, there are 4 outcomes in which that happens, and so that's just 4 out of 36. So the probability of event A happening is 4 out of 36. So sometimes, in statistics, we're a little bit less worried about reducing fractions. So we can leave it as 4 divided by 36. Sometimes that's a little bit nicer because we can see more clearly that there are 4 outcomes out of 36 total outcomes. And, in other math classes, we'd be like, oh, you have to reduce your fractions, right? That 4 out of 36 must be reduced to 1/9. We're not so picky about that here. And in some ways, the 4 out of 36 is kind of nicer. Okay. All right. So now let's talk about what's the probability of event B. Now, B is the sum is not a 5. So we think about B, the event B, as being the complement of A. So what is the probability that A happens, that we don't get a 5? Well, there's 4 ways to get a 5. So how many ways are there to not get a 5, right? So you're either gonna get a 5 or you're not gonna get a 5. So we have those 36 outcomes are broken into 2 groups, right? 5s, sums that are 5s, and sums that are not 5. So we can simply take the probability of getting a 5 and subtract that from 1. And that would give us the probability of not getting a 5. So that is our complement rule. So the event B is the complement of the event A. We can essentially say either we're going to get a 5 or we're not going to get a 5. So we sort of break these, we break the event space up into 2 parts. Some basic rules for probabilities. So the probability of any event happening is between 0 and 1. 0 means that the event is impossible, so it could be that. The probability being, if the probability is 1, then that means it is certain it will always happen. So it's got to be somewhere between those two. Can be equal to 0 and 1, but often it doesn't. I mean, because, certainty and never happening generally, when we're talking about probabilities, you're going to find that often those aren't the case, but they are possible. Okay, so if we took all the probabilities of all the events that make up the sample space and we added up all those probabilities, they would, of course, sum up to 1 because that's the list of all the possible outcomes. And so if we added up all the individual probabilities, they have to add up to 1. And so if everything is equally likely, then calculating the probability is like we saw with the 2 dice example. It's the number of outcomes that are possible, like the sum of 5. There were 4 outcomes that had 2 dice that summed to 5. And so it was 4 out of 36, the total number of outcomes in that sample space. And then we talked about the complement rule. The probability that an event does not occur is equal to 1 minus the probability that it does occur. And let's see what else. If 2 events are not have no outcomes in common, so you'll see in a minute that that's called mutual exclusive. If they don't overlap, then we can simply add up the probabilities that one or the other happens. So add those up. And that will give us the probability that both things happened. That either thing happens. And so we simply add up those probabilities. And of course, that's only when the events don't overlap. There's no way to have them both happen at the same time. And so this is what this last thing is saying here, really the same thing. So if the events are mutually exclusive, sometimes referred to as disjointed, that means like the sum of getting a 5 or the sum of probability that you'd get a 5 or a 7 on the sum, right? Those don't overlap. So you could add up the number of outcomes for each one and simply add them up. So if they have none in common, then the probability that they both happen at the same time is going to be 0. The probability that one or the other is just going to be the sum, and we'll talk about that in a minute. But the probability that both things happen, so when you roll 2 dice, for example, you can't get both a sum that's a 7 and a 5. So the probability that those both happen would be 0. Okay, and so we refer to that as mutually exclusive. the two events cannot simultaneously happen. All right, so kind of like another way of looking at some of these same rules. First one, then, probability of any event is between 0 and 1 inclusive, so it could be 0 or 1 or anything in between. If we look at the probability of S being the sample space, the sum of all of them has to be 1. And then when all the outcomes are equally likely, it's simply the number of outcomes divided by the total the number of outcomes that correspond to our particular event divided by the total number in the sample space. And then the complement rule, you can see here that so the A with a superscript C means the complement or not A happening. So the probability of not A is, so here the probability that A does not happen is denoted as A with a superscript C to it. So it's the complement of A or not A, either way, is 1 minus the probability of A happening. Okay, and then the mutual exclusivity that we were talking about, probability of A or B happening is a probability of A plus the probability of B. Now, of course, that means that they have to be mutually exclusive, right? They can't both happen at the same time. So this would be, what's the probability that when I roll two die, what's the probability that I get a 5 or a 7? It's the probability of 5 plus the probability of a 7, okay? Because those would be mutually exclusive events. Sometimes we'll use a two-way table to help us with some probability calculations. So when you're looking at two different events, this, it can sometimes be helpful. So here's an example that we see in our book on page 309. So suppose we have students, right? We have 178 students, and we ask these students, first of all, what's your gender? And then we also ask them, is your ear pierced? Do you have pierced ears, I guess? And they said yes or no. Okay. So if we randomly pick a student, one of these 178 people, then we want to find the probability that that particular student has pierced ears. So we're going to define the event A as being that the student is male, and define the event B as the person has pierced ears. All right, so the probability that a person has pierced ears, randomly chosen, find that probability. So what's the probability I randomly pick somebody and that they have pierced ears? All right, so if we look, we have, the people that we're considering as being a success here, having pierced ears, are the 19 males and the 84 females in that first column that said yes. So that's 103 students have pierced ears. So the probability of randomly choosing a student, one of the 178 students that have pierced ears, is simply 103 divided by 178. So sometimes we'll leave that as a fraction. We can convert it to a decimal, or we can then take that decimal and write it as a percent. So probabilities answers can be written as fractions, decimals, or percents. All right, next one, B. What's the probability that the person we randomly picked is a male with pierced ears? All right, so this is going to be looking at just those 19 males. So it's like they have, we know they're in that column with 103 because we know that they have pierced ears. We want, well, it's not really that, sorry. It's, think of it as the intersection of male and pierced ears, because if we think about a male with pierced ears, so the way we say that, it really means what's the probability that you randomly pick somebody that they're a male and they have pierced ears. So it's sort of the intersection of the column, which is yes, having pierced ears, and the row that says were male. And so the intersection of that row and column is simply that 19. And so it's the 19 divided by the 178. Okay. And again, you can write it as a fraction, a decimal, or a percent. All right, so now let's go on to C. Find the probability that the person we randomly choose, the 178, is a male or has pierced ears. All right, so that's going to be, we want to think about they can be in that column that is male, or they can be in the row, the row that's male, or the column that is yes to pierced ears. However, we can't add up 90 and 103. Well, because first of all, if we add up 90 and 103, that'd be 193. That's more people than are even in, in this little example. And the problem with that is that we counted the 19, the males with pierced ears, we counted them as males, but we also counted them in the column for pierced ears. So if we, so in other words, these two events, male and pierced ears, are not mutually exclusive. So we have to be careful. We can't just add up 90 over 178 and 103 over 178. That would give us a total that is greater than 1. So that would not work. All right. So, the simplest way is probably just to add up 19 and 71 and 84. Those three numbers would total the 174. Another way you can do it is you could do the row total, which is 90, and the column total, which is 103. But then you'd have to subtract away a 19 because that 19 got counted both in the column and in the row. So ultimately, it's everything but the 4 people who are female and don't have pierced ears. So 174 over 178, a decimal 0.98, or the percent, 98%. Okay, so addition rules for 2 events. And so if the events have no outcomes in common, like those 2 events we just talked about, males and pierced ears, well, there were some males, there were some students that were male and also had pierced ears, so they were not mutually exclusive in the last slide. All right, so we can also look at the situation, instead of just looking at a two-way table, we can look at it as a Venn diagram. So we can think about event A being that you're male, and we can think about event B being that you have pierced ears, and then the green space in between is the people that are male and have pierced ears. Okay, so that would be so the overlapping of those 2 circles. So that green space kind of represents those 19 people. They got counted for having pierced ears. They got counted for being male. They got double counted. So that's why we had to be careful. We couldn't just add the probability of A plus the probability of B, because these were not mutually exclusive events. Okay, so when we generally add things and we are concerned about adding 2 events, it's so in other words, the probability of A or B happening, it's probability of A plus the probability of B if they're mutually exclusive. But if they're not mutually exclusive, then we have to subtract away the probability of both. So that's that green space in the middle, because the green space got counted in the blue circle. It also got counted in the bright yellow circle. And so we would have to subtract one of those greens away if we simply just add up the 2 probabilities. All right, so some ideas about Venn diagrams and how we can demonstrate the probabilities with Venn diagrams. So the circle, the white circle, is the event A, and then the green space outside is not A, or the complement of A, so that we denote that with A and then with a superscript of a C on top. So that's the complement of A. It's everything not in A is the complement of A. All right, and then this second Venn diagram here shows that event A and B are mutually exclusive, or sometimes referred to as disjointed. They don't overlap, so you can't be A and B at the same time. So this would be like in the example in the past, if that we just did, if no males have pierced ears, then the event A that you're male, and event B that you have pierced ears would not have anything in common, so that they would be mutually exclusive. That was not the case in the previous example. All right, so this Venn diagram shows the intersection of A and B. So that means that green space, in the green space, B occurred, but also A occurred. So event A and B happening. So that sort of upside down U represents the word and it's an intersection. So if we say A intersection B, that means, or A and B, it's the area of overlap between the two events. And then here is the probability of A or B. And notice these are not disjointed. These are not disjointed. These are not mutually exclusive. These two events overlap. And so we say the probability of A or B, the union is what we refer to this sometimes as. So A union B, or event A or B happening. So that means that we have either you can be in A, or you can be in B, or you could be in both if we say A union B, okay? And so just to kind of help you remember, the thing that looks like a U stands for a union. The things that looks kind of like a lowercase n stands for intersection. All right, so let's go back to this example for pierced ears, and let's create a Venn diagram. So fill in your Venn diagram. Remember that A is the event you're being a male. B is the event that you have pierced ears. Fill in the numbers from the table in the different shaded regions, in the 4 shaded regions. All right, so you can see that the yellow crescent, meaning you are male but don't have pierced ears, right? That's the 71. Together, the 19 and the 71 make up the total of 90 males. The blue crescent, 84, that's females that have pierced ears. Together, the 19 and 84 add up to all the people that have pierced ears. So the one circle represents event B, so that's 103 people that have pierced ears. And then, of course, the green intersection is both male and having pierced ears. So it's the overlap of them. And then the 4 outside, that means you're not male and you're not female. You're not male and you do not have pierced ears. So it's the non-males having pierced ears. Okay. Oh, I'm sorry, having not pierced ears. Okay, so some more symbols, like how could we write these? Now, don't get too overwhelmed by these symbols. You're not required to really understand these symbols here. They get a little bit intense. So in the intersection of the two circles, male and pierced ears, that's that count of 19. What symbol would be used for that? Well, that's just A and B. All right, inside circle A, but outside circle B, that would be that yellow crescent. This is males that do not have pierced ears. And so that would be A intersection not B. So the intersection of everything outside of B and A, so that would be the 71. So A intersection not B, or the complement of B. All right, inside circle B, but outside circle A, so that would be the blue crescent. So that would be the intersection of B and not A. Or in this, doesn't really matter the order. In this case, they said not A and the intersection of that and B. So that's the 84 people. So that's the people with pierced ears that are not male, right? So that's the females with pierced ears. And then outside both circles, that would be complement A, the complement of A, intersection complement of B. So not in either one. Here we're going to use Venn diagrams with a table to sort of practice another example. So in an apartment building, 40% of the residents read USA Today, the newspaper USA Today, and 25% read the New York Times, and then 5% read both papers. And then we choose a resident from the building at random and ask them what paper they read. Okay, so we want a two-way table, and I've sort of already begun it for you here, that displays the sample space in the situation. So like fill in all the numbers, right? So we have 2 by 2 and then also the column and row totals. So fill in that table based on the information they gave us up above. 40% of the residents read USA Today, 20% read the New York Times, 5% read both. Okay, so let's see what we got here. So both would be sort of the intersection of yes, USA Today, and yes, New York Times. So that's where we got that 5%, 0.05. And then 25% of them read the New York Times. So that's over in the row total for yes, New York Times. And then the column for yes, they read the USA Today is 40%, so 0.4. All right, so with that total, with those things in there, now, of course, in this case, these are percentages, not counts. And so the bottom right corner is 1 or 100% if we were writing this as percents. All right, so using that, we should be able to fill in the rest of the table. So spend a second doing that. All right, so now let's do part B, construct a Venn diagram that represents this situation. We'll call the yellow circle on the left event A, which means they read the USA Today newspaper, and B being the darker circle on the right, that is they read the New York Times. So in this case, we're going to put in percentages because we don't have the counts in our table. In this case, this table has percentages in it. So take a second and put in the values in those 4 regions. So when we say that, we mean this region in here, the blue crescent, and then this sort of tan out here. All right, so you can kind of see, you're breaking up those percentages. The 5% was the intersection, right? 5% of the people did both. And then we knew this whole thing, this whole circle was 40%. So we know, of course, this had to be 35. And this whole thing was 25%. So this had to be 20. And then what's left after we add up these 3 is that this had to be 40%. Read neither of those 2 papers. Okay. All right, so now C, find the probability that the person reads at least 1 paper. So that means they read one or the other or both. All right, so that's pretty easy. You can really think of it as just adding up those 3 values, this one, or this one. Or you could really use the complement rule and say it's everything but this. So it's not 40%. So the not, the negation or the complement of that 40%, that would be everything else. All right, so you could have subtracted that from 1, right? So 40% taken from 100% is 60% or 0.6. All right, D, find the probability that the person does not read either paper. All right, so that's simply this tan region out here, and that's represented by that 40%. So that would be 40%. Again, don't really worry too much about this notation here with not A intersection not B, or complement A intersection complement B. Don't worry too much about this notation. They're not really going to require you to know that and use that. All right, so this takes us to the end sort of these notes, and then this is the homework for section 5.2. But let's just go through one more example while I have your attention. All right, so let's say we are rolling 2 dice. So one gambling game that they often play in Vegas. I've never played it and I don't really understand all the rules, but is craps. And so you're rolling 2 dice, and my understanding is that it's really good when you first roll the dice if you get a 7 or 11. So let's first think about 7. So what is the probability of getting a sum that is 7 when you roll 2 dice? And again, I have the sample space displayed there, so it kind of helps you. So the probability, these are the ways of getting 7. There's 6 ways of getting a 7. And so that would be 6 out of 36, or 1/6. And then an 11 is also considered a good roll for your first roll. So 7 or 11 is what you want. And so what's the probability of getting a 7? An 11. All right, so that's only 2 ways to get that. So now what's the probability of getting a 7 or an 11? We could simply add those up. So in this case, it would probably be easier if we left them as 6 over 36 plus 2 over 36. So that is going to be 8, because these are mutually exclusive. The roll can't be a 7 and an 11 at the same time. So we simply need to just add those up. So 6/36 plus 2/36 is 8/36. And then I went ahead and reduced it to 2/9.